Hey guys, I hope you're doing well. This is just a kind of the introduction to lab 10, the last lab that we have here. And I'm just going to kind of walk you through at least a couple of important things to remember when we're kind of going through this and kind of think about what we expect for each one of these problems. This is actually a more straightforward lab than we have in the past. It's a little more procedural. I just want to kind of just go out and kind of just say exactly what we're going to do here. So this lab is going to tackle, as we see up here, parametric surfaces and surface integrals. For the first part here, we're going to ask you to kind of go through and start to try to plot parametric surfaces. And we're going to work with that. So I want to just remind you what a parametric surface is. A parametric surface has two variables, and it kind of describe a surface with two variables. We can do that. We describe a volume with three variables. We describe a curve with one variable. And so what we want you to do here is we can write a parameterization usually very easily. We'll walk you through an example here, so I'd highly suggest you kind of just walk through this for yourself. But for instance, if I wanted to parameterize a part of a cylinder S, which is x squared plus y squared equals 64, that lies between -1 and 3. Kind of just like kind of a half cylinder, not a half cylinder, but no, a full cylinder, but just kind of like that. There's a couple different ways we can describe it. Probably the best way to do that is with points like cylindrical coordinates, right? We have r cosine of theta, r sine of theta, and z. And we note that since I'm on my surface of my cylinder the entire time for that, we know this r has to be a constant. So we can use just the parameters theta and z and create point something that looks like 8 cosine of theta, 8 sine of theta, and z. And so therefore, we can have our parameterization as this, where u goes from 0 to 2 pi, v goes from -1 to 3. If you don't like how we write for u and v here, you can also just use theta and z. It's absolutely okay to do that. The way I usually do my videos, I usually use this, especially if it's a natural extension. Sometimes u and v is just a little bit easier to write. But in terms of theta and v, that's totally okay. Theta and z is okay here. Now, how do we visualize these things in Mathematica? Well, we can define our parameterization, making sure we use vector notation here, kind of using that. And then we use parametric plot 3D. So parametric plot 3D will allow you to parameterize your curves in 3 dimensions. You take our uv, and you just tell it I want to run from 0 to 2 pi, because it's a full cylinder, and then v goes from -1 to 3. And it'll plot this. And what's really, really interesting is it will show you the grid curves that you're drawing. So the mesh that Mathematica draws here will show you the grid curves. And what I mean by grid curves, let's say I let v be a constant and I move u. What curves are made? So for instance here, if I keep v constant, I'm at a same height, right? And I'm just moving u, which is just moving in the circle. So I should expect that I'm going to get circular grid lines. And also, if I keep u be constant and I move v, x and y stay the same, but I just move v linearly. So I should expect lines, just vertical lines in that case. So you should see that in Mathematica, you're going to have circles and you're going to have lines in your representation of that. So sometimes it's beneficial to maybe use some other variables here. You can also use t and z if you wanted to. There's the other way you can do it too. So this first couple of exercises are going to be you just trying to understand how to use Mathematica to do this. The first one, we're going to ask you to kind of do this paraboloid in 2 different ways to parameterize us in terms of x and y, which is usually very, very easy. But it becomes a little bit complicated when we're trying to come up with a domain. And then in terms of R2, we're going to ask you to just use r and theta to parameterize this paraboloid here. So again, think about things, especially you think about A, project onto the xy plane. For B here, definitely so to come up with polar coordinates. Think about, again, your projection onto the xy plane. What is actually going to be happening there with z's between 0 and 4? And then what we're going to come up with again here is we're going to start to think about the normal vector. So we're going to need to calculate this for a lot of our surface integrals. And what we want to do here, RU cross RV, we can use this with the cross command. Where I have my parameterization, I have d with respect to u and d with respect to v. I want to be very careful here. Please do not include a colon here. I have this little bit of a thing right here that says, for the love of God, please do not put a colon. So if you put a colon here, it becomes very, very just weird. And it messes everything up. So make sure if you're going to suppress the output to put the semicolon at the end. And then you can just use a simplify command. It just helps clean up sometimes terms that Mathematica doesn't simplify it, but it's not necessary at all for a regular computation. Exercise 2 is for you to plot this surface and then come up with the R of UV for this, but also come up with what is this surface itself. Before you even plot it, come up with it. Think about, what is U and V representing here? Where have you seen this type of thing before? And also come up with maybe what this domain looks like. This should be just a comment. So don't plot it and then do that. Try to do A before B and then kind of go back and see why you could do it. Then we're going to come up with surface areas. How do we come up with the surface area of a parameterization? We know the area of S can be computed with this double integral where we take the magnitude of RU cross RV. So we take our cross product and we take the norm of it. So this is going to be kind of how we do that. So if I have some surface here of 3x plus 2y plus z equals 2, where x is between 0 and 2 and y is between 0 and 3, something like this, we can set up some evaluation like this here, where I let R be my parameterization. I can let this be x and y. Kind of walking through that, right? If I have something of the form z is equal to a function of x and y, I can let the functions just be x comma y comma that function itself. So we set up our parameterization here. We can then calculate the norm here. I've actually realized that this colon should not be there. It's actually really important to say there that colon shouldn't be there, and I'm gonna have to fix that. So I'll apologize. And then we integrate the norm of this normal vector, right? We're trying to calculate the magnitude. And we go from u from 0 to 2 and v from 0 to 3. You can also just include everything in a 1 if you wanted to, these last two lines, where you do the norm of the cross product. Whichever one you want to do, whichever one's a little bit easier for that. And so again, exercise 3 and exercise 4 are just kind of going through that. Find a parameterization for your curve and then find the surface area. Do not include this colon here. I'll kind of change that in the lab specifically, but so we at least have some more formality there. And lastly here, integrals of vector fields, the flux integrals that we're kind of discussing, right? Something that looks like this here. I would definitely suggest you read through this, but basically with the same, we're going to calculate the flux integral, the amount of fluid that goes through the surface S, where F is the fluid motion. If we parameterize this surface, we can actually calculate it this way. So over my domain D, I plug in for F here, I plug in my parameterization, and I take the dot product with my normal vector, RU cross RV, over my dA. So the process is as follows. We parameterize our surface, figure out our domain. We calculate the normal vector, RU cross RV. We then substitute an F of R of UV, which we can do with the at symbol. Remember last time, we can't do this, right? We can't do F of R UV, we can't do F of R of T. We're just F of R of U of V here. And lastly, we're going to compute this integral by taking the dot product of my F at RUV and then plugging in and dotting with the normal vector specifically. And so just going through this, in this first example here, we talk about specifically what this is in the first octant. So make sure you're kind of thinking about your theta components, thinking about that just in general. And we parameterize our surface, make sure you change your parameters. I want you to show what this looks like, just to kind of make sure we're all in the same field. Define this vector field F here, superimpose it. Make sure you define this vector field, just X, Y, Z. It's actually not too bad of an, it's just a radial one. And then we compute the normal vector, give it as normal 5. Make sure you don't use the colon. I apologize for saying that again. And we take the dot product. So we have F at, this is where this F at comes into play, F at of R5 here, and we dot it with the normal vector in this case. And cha-cha slide. Why not? Have some fun. And then this last one here is just kind of combining everything into one problem to kind of do the same exact steps as you just did in exercise 6. So that's basically it. So I'm going to go ahead and change that actually while you're watching me here. Give me a second. I'm going to go ahead and do that right now because that's actually really bad that I had that in there. Something like that. Yep, something like that here. I will change that then. And now there is no colon. And there shouldn't be a colon. I was bad. So there we go. Okay, let me know if you have any other questions about this. I'll see you in lab, but I hope you're doing well, and I'll see you soon.